So we will see the concept of electric field intensity to this session. So what is electric field intensity, and how do we mathematically find how to calculate the electric field intensity due to a charge and different types of charge configurations. So all these topics we will learn today. So electric field intensity, by its definition, it is basically the force on a unit charge, we can say. So we have seen the as per the Coulomb's law, we can say that the force due to a point charge, that is F, the force between 2 point charges, F is equal to, in the vector form if you write, it is nothing but Q1 Q2 divided by 4 pi epsilon, and the distance vector between the two charges, that is R12, the magnitude of that square. That's basically the distance between the two charges, and the direction of the vector, the force is in the direction of the in the charges. We will write it up R. So this is the force equation based on the Coulomb's law. When you talk about electric field density is basically due to a charge or a combination of the charges. So let us assume that there is a charge Q1 present at some point in space, and due to this charge there exist electric fields around the charges, and at any point, if you see, at any point, so let us take an example at point P. At a point P, there exists an electric field intensity. So the electric field intensity at this point P, that we will write it as maybe E at the point P, okay, which is nothing but the force per unit charge, we will say, like, or in the by the definition we can say electric field intensity is equal to force acting on a unit charge, or by its definition force acting on a unit charge, we can write it like E is equal to the vector E is F by Q, or in terms of the charge itself, if you write, due to a point charge, electric field intensity at a point P can be written as, in this case, Q divided by, so due to a point charge, we can say the electric field intensity due to a point charge is equal to Q. Q is the charge itself. So in this case we have written Q1, right? Yeah. So Q1 divided by 4 pi epsilon, the distance between the point and the charge, where this is the distance R now. So we will say R square. So R square, and the direction of the electric field density is in the same direction of this line connecting the point and the charge. So that is, we will write as. So the electric field intensity, by its definition, as we said, it is force acting on a unit test positive charge by the definition. And we have seen if there is a point charge which is denoted by the charge Q if it is present, and at a point P, suppose here is a point P, there exists an electric field. So that electric field can be written as maybe E at this point P, which is E P is equal to Q divided by 4 pi epsilon R squared. R is nothing but the distance between this charge and the point where we are measuring the electric field intensity. So that is R. So the square of the distance, and the direction of that electric field intensity is in the direction of the vector R itself. So we can write it as the AR as the direction vector. This is the electric field intensity due to a point charge. So now when it comes to multiple charges, suppose if there are n number of charges present, like Q1, Q2, Q3, Q4, like that, up to Qn, there are n number of charges. In such cases also we can say at a given point P, so let us take the point P somewhere here, okay, at this point there exists electric field intensity due to the effect of all these charges. So that can be, we can find out that by obtaining the electric field of the individual charges. For example, the electric field due to Q1, let me call it as E1, and that is in the direction of this line what we can see here. So that is E1, and the field due to Q2. So let me write it as Q2 here. This is Q2, this is Q3. Okay. So Q2 is in the direction, maybe this is the direction of QE2, okay. Like this. Up to we have n number of charges, so we will be writing up to En, and this is En. So now the total electric field, that E total we can say, okay. The total electric field is the vector sum of the individual electric field, that is E1 plus E2 plus E3 plus E4 we can say. E2, E3 like that up to En, and all these are the vector sum, so we can put the vector symbol on top of that. So now we know that the individual electric field, for example E1, we can say it is nothing but Q1 divided by 4 pi epsilon R1. Let me call the distance between Q1 and the point P is R1. Similarly Q2 and the point P is R2, then Qn and point P is Rn, and there exists a vector also associated with each distance. So that distance square for E1 it is R1 square, and A-R1 we can say, or A1, you can use your own terminologies. Similarly, we have E2, which is Q2 divided by 4 pi epsilon. There is an epsilon here, epsilon R2 square AR2. Like this, we have up to En, which is nothing but Qn divided by 4 pi epsilon Rn square Arn, we can say. And please remember the unit for the electrical intensity is volts per meter. Okay, volts per meter. This is the units for electrical intensity. So the total electric field intensity E total, we can say it is E1 plus E2 plus E3 plus En. Okay, E1, E2 like that up to En, and if you substitute the above equations, we can say it is nothing but we can finally write it as 1 by 4 pi epsilon, which is common for all the electric field intensity terms, provided the medium is the same. There is a uniform and homogeneous medium units. Then 1 by 4 pi epsilon can be, then we can put it as a summation with an index I is equal to 1 to N we have used, right? Yes, 1 to N. Qi divided by Ri square, and which will give rise to the direction also. So I will write it as maybe I. Okay. So this is the electric field intensity due to N number of charges. Okay. Due to N number of charges. So when it comes to charge configurations, for example, like there are in reality or practically we don't get to point charges as such. The point charge is basically an approximation of approximation, basically we can say. So, but when it comes to real scenarios, we will be getting charge configurations like line charge, or a surface charge, or volume charge. So these are the different types of charge configurations we will come across. So under each cases, then correspondingly we can say the electric field intensity we can define as E is equal to, in case of a line charge, we have a concept called line charge density, which we use the notation rho suffix L. Okay? This is the line charge density we can say. So naturally, the total charge is charge density into the total, either it is length or surface area or the volume. So if it is line charge, then the total charge Q can be written as rho L. Basically integral rho L dl, because line may not be always a linear and symmetric line. So we will use the notation integration there. When it comes to a surface charge, the charge density is rho s, and the total charge can be written in terms of surface integral rho s ds. And remember, surface integral is nothing but double integral. And when it comes to volume charge, the charge density is rho v, and the total charge can be written as surface volume integral rho v dv. So this is about the charge configuration. So in such cases also, what is the electric field intensity? If you see, when it comes to line charge, it is nothing but wherever the q is there and this integral is there, we can replace q and summation are there. We can now replace that with integral notations. So we can write the total electric field due to a line charge is that is E is equal to instead of q we will be writing rho l dl. So integral rho l dl divided by 4 pi epsilon r square AR, okay, volts per meter. Similarly, for a volume charge as well as the surface charge, we will get equivalent equations like this. Okay. So with this concept, let us now go and see how to find the electric field intensity due to an infinite line charge. So let us take that problem. So we can write it like the electric field intensity due to infinite line charge. So here we will consider infinite line charge, which is extending from maybe minus infinity to plus infinity. For the convenience to solve the problems, let us consider that line is nothing but lying in the z-axis. So let us draw a z-axis from top to bottom, and which is ranging from minus infinity to plus infinity, and somewhere away from this point, this line, we will consider a point, and that point which is vertically at a distance, the perpendicular distance between that point and this line is let us call it as rho. Okay, rho, because we will be using the cylindrical coordinate system in this example to solve this problem. So let us consider rho as the cylinder, as the radius of a cylinder. So the same rho is the perpendicular distance, and let us consider a small portion on the top of this line, which is contributing a charge which is called dq. Why it is called dq? Because the entire line consists of the charge q, and a small portion of that line we are considering now, which is considering the dq. And we have seen that earlier from the definition of line charge density, like we can say that the charge q, or now in this case we can say the dq is nothing but rho l into dl. In the previous definition, I think I must have used the q is equal to integral rho l dl, right? So this is nothing but integral dq. So dq is nothing but rho l dl. So now rho l is charge density, and dl is nothing but the dl in the z direction, because if you are using the direction as z here, then we can say dl is dz itself. So the vector dl can be written in terms of dz in the z cap also. So anyway, we don't need the vectors notation here. Let us avoid that. And now from that dq to this point P, let us draw one vector which is in this direction. Let me call this as vector r. Okay. So what we will do is, like, we will consider this dq as a point charge, and we already know the expression for the electric field due to a point charge, which is E is equal to q by 4 pi epsilon r square AR. So we will use the same equation here also, but instead of q, we can use dq here, because dq is the point charge in this case. So we can write the electric field intensity due to the point charge is equal to, at this point P, let me call this point as P, the E is equal to, instead of q, we will write dq. So dq divided by 4 pi epsilon r square AR. This is the direction as well as the equation for the electric field intensity. And now what are the things you need to be knowing here is what is this vector r, so that only then we can find the magnitude of the vector as well as the direction of the vector. So what is this vector r? In order to do that, what we will do is we will make it very simple. Let us consider this as the center point, because anyway it is an infinite line charge, so any point can be considered as a center point. So let us consider this is a center point where in the cylindrical coordinate system we know the variables are rho, phi and z, right? So these are the variables. So let us consider all the three variables are 0, 0, 0 in the center point. And let us take the rho distance away from this at this point here. So at that point, let us consider rho is rho itself, and for convenience we will take phi is equal to 0 and naturally z also 0. So this is rho 0, 0, 0, 0, 0, and we have one more point on top where this dq is present. This dq is present. At that point, you know, we can consider rho as 0 because there is no distance between that point and the axis here. So rho is equal to 0, and phi also we will use as 0, and z we will consider it as z itself. So these are the coordinate values in the cylindrical coordinate system with respect to the vector r and this center of this axis. Okay. So now we can easily write what is this vector r. Vector r in terms of rho, phi and z. So if you see, vector r is rho minus 0 in the rho direction, then 0 minus 0 in the phi direction, and 0 minus z in the z direction. So we will write it like rho minus 0 means rho in the rho direction. So rho cap. So rho cap means it is direction vector. Okay. Then 0 minus 0, 0. Then 0 minus z direction means minus z cap. So this is the vector r itself. So now if you see, if I substitute this vector r in this equation, okay, what we will be getting? We will get E. So remember one thing, there is a small problem in the sense, here we are using dq here, right? So the electric field obtained due to this dq is not the total electric field, but it's the dE. It is differential electric field, we can say. Okay. So the total electric field is integral dE. Okay. Anyway, so we will rewrite that equation here. So we can write dE is equal to dq. Instead of dq, we will write rho L dL, or instead of rho L dL, we can write rho L dz. So that is dq, rho L dz divided by 4 pi epsilon remains same, and instead of r square, now we will write rho square plus z square. Basically, magnitude of this vector is square root of rho square plus z square, right? So the square of that is the rho square plus z square itself. So that is the And when it comes to the direction is, say, vector divided by the magnitude of the vector, or we can write rho cap minus z cap by 4 pi epsilon rho square plus z square, the square root of that, or 1 by 2 we can write, right? Sorry, there is this 4 pi epsilon there. Yeah, so this is the unit vector. This is the unit vector. Okay. So now when you see, when you combine all these things, finally we can write it like dE equals, I will write here, rho L dz by 4 pi epsilon rho square plus z square into rho square plus z square power 1 by 2, we can write as 3 by 2. Okay. Then rho cap minus c cap. Is it? So this is the dE. So now if this is dE, we can say total electric field E is equal to integral dE we can say. So when you are doing integration, basically the variable here is dz. Z is a variable. So integration is ranging from z value ranging from minus infinity to plus infinity. That is what we have seen here. Z is ranging from minus infinity to plus infinity to get this total line, infinite line, right? So now when you do this, we can write this is equal to integral, okay, rho L dz. So from minus infinity to plus infinity, rho L dz by 4 pi epsilon rho square plus z square power 3 by 2 rho cap minus c z cap. This is the expression for the electric field intensity. Finally, now in order to solve this, what we can do is you can see the if you observe one thing here, let us consider a point on top. That as we have seen here, we have now considered a point on top. Equivalently, a symmetrically opposite point, like somewhere here, exactly at the bottom, if you consider another point, and there will be an electric field due to that point, right? So let me use a different color here so to represent that point. The bottom point is green point, okay? So let us call this is dq1 and this is dq2, and due to this dq2 there exists another electric field, okay? You can say that electric field is in this direction, and due to dq1 the electric field is in this direction. So you got dE2 in this direction and dE1 in this direction, right? So when you see this way, when you add these two vectors, you can see that the z component of the vectors will get cancelled, right? So for dE2 the z component is towards top, and for dE1 the z component is towards down. And since both are like dq1 and dq2 are same in magnitude, the z components will get cancelled. So that means what we can say is after you do the integration from minus infinity to plus infinity, basically integration is nothing but adding, right? Adding all small points, right? So when you do that integration, while adding this value and this value, the net result will contain only the rho component. Similarly, because of that, we can use that idea now itself while solving the problem. So what we will write is, we will take this is equal to integral minus infinity to plus infinity rho L dz divided by 4 pi epsilon rho square plus c square power 3 by 2 rho cap. Why z is eliminated? Because z will get cancelled after the integration anyway. So we will not use that while doing this problem in the beginning itself. Okay, so this is the total electric field intensity. So now since this problem can be now easily resolved by doing some substitution. So what is that substitution? If you see, consider this the value. Suppose this dq is going from this point towards minus infinity, then you consider an angle here. Let this angle be theta. Okay, so this angle theta will tend to plus 90 degree or minus 90 degree because it is below, right? So it is going to minus 90 degree as this z tends to infinity, minus infinity. So basically the substitution what we can do is, the substitution is this one. You take this is rho, right? And this distance is z. This is rho, this is z. So this theta can be now written as tan theta is z by rho, right? So tan theta is z by rho. That's the substitution we will do. Tan theta is equal to z by rho, or we can say rho is equal to, z is equal to rho tan theta. So this is the substitution we are going to use it. So what happens is, when z equals minus infinity, theta will become minus pi by 2, and z equals plus infinity, theta will become plus pi by 2. So this is the limit updation also we can see. So now with this idea, if you do the substitution, so we can say if z is equal to rho tan theta, z is equal to rho tan theta, we can say in the denominator we have a term rho square plus z square, right? So rho square plus z square we can write it as rho square plus, instead of z we will write rho tan theta, so rho square tan square theta. So this will become the term rho square plus z square will become this one, or this is nothing but rho square into 1 plus tan square theta, and 1 plus tan square theta is nothing but 6 square theta, right? So rho square into 6 square theta we can write. 6 square theta, okay? And dz, so if you see on the numerator we have a term dz, right? So that dz term will become, if you find dz from this equation, so we can write dz is equal to rho 6 square theta d theta. For rho tan theta, if you find the differentiation, it is 6 square theta d theta. So now when you do the substitution of these two substitutions, if you do for the above equation, then we can write E is equal to, okay, we have integral minus infinity. Instead of minus infinity, we will be having, instead of minus infinity, we will be having minus pi by 2 to pi by 2, because now z is changed to theta, and we have on the numerator rho L dz, right? So what we will do, we will rewrite this once again so that no need of scrolling. So this was our equation. Now what we are doing is, this is equal to, after substitution, right? After substitution, we get integral minus pi by 2 to pi by 2 rho L dz. Instead of dz, we will write rho 6 square theta d theta into rho cap. There is a rho cap here, right? So that is getting the numerator, divided by 4 pi epsilon rho square plus z square is rho square 6 square theta. We have seen that, right? So rho square 6 square theta, rho square 6 square theta power 3 by 2. So that will become rho cube c cube theta. Is it so? So we can, I will write it once again for simplicity, minus pi by 2 to pi by 2 rho L. Let me take rho together. So rho square, there is a rho here, there is another rho here. So rho square 6 square theta d theta divided by 4 pi epsilon. When you do this together, when you take this 3 by 2 inside, then it will become rho cube. So rho cube c cube theta. So that's done, right? And the direction is rho cap. So now things are very easy now, because there is a rho square on top and there is another rho square on bottom, which will be making this as rho, and there is a 6 square theta here, which will be, we can eliminate that also, 1 by 6 theta it will become. So finally this equation will come down to the form what you are writing here, integral minus pi by 2 to pi by 2 rho L d theta divided by 4 pi epsilon. So instead of 1 by sec theta, we will write that as cos theta. 1 by sec theta is cos theta, right? Yeah. So we will write that cos theta on top. So we can write it like this. Rho L cos theta d theta, then 4 pi epsilon rho in the rho direction. So this is the equation we will be getting. And now if you see, the variable is theta, So rho L, rho, 4 pi epsilon, all these are constants. So we can take out those things outside. So rho L divided by 4 pi epsilon rho integral minus pi by 2 to pi by 2 cos theta d theta in the radial direction. This, once you do the integration, this term will become integral cos theta is minus sin theta. So you will be getting minus of sin pi by 2 minus of sin minus pi by 2, right? So this will be the integration term. So sin pi by 2 is 1, so minus 1 minus. So when you do the integration of this entire term, you will be getting the answer as 2 pi. Okay, 2 pi will be the answer for this. So finally we can say this answer is equal to rho L into 2 pi divided by 4 pi epsilon rho cap. So this is the E, which can be simplified as this is 2. So this is not 2 pi, this will become 2 actually. So this term, as we said, this will become 2 after doing the integration, and that will give rise to the final answer 2 into rho L divided by 4 pi epsilon rho in the rho direction, or that is the final equation we can write. Electric field intensity due to infinite line charge is rho L divided by 2 pi epsilon rho, which is the perpendicular distance between the infinite line charge and the point where we are measuring the electric field intensity, and the direction is the radial direction. Okay, so this is the electric field intensity due to an infinite line charge.